students, today we are going to discuss couple per unit twist of a cylindrical wire. So we will be deriving the expression for couple per unit twist on a cylindrical wire. For this we have considered a cylindrical wire like this, and it is of length small l, and the radius is small r. Okay, now and the coefficient of rigidity for this material of the cylindrical wire is eta, and now we will be considering that this upper end of this wire is fixed, and we are applying and a couple is applied in a plane perpendicular to its length at the lower end. Okay, at the lower end, and perpendicular, it is applied in a direction perpendicular to its length. Now we need three figures in this case. So to derive the expression for couple per unit twist for this cylindrical wire, we will have to consider that inside this particular, this is a solid, this is basically a solid cylinder. Okay, so what we will be considering, inside this solid cylinder we will imagine another cylinder, coaxial cylinder, and the axis will remain the same. Fine, and we are going to consider another coaxial cylinder like this. We are going to imagine. And this coaxial cylinder, actually if you look from this direction, if you look from this direction, okay, so it will look to you like you can see like this, or I will rather make it. So if you look from that direction, the cross section of this particular wire will look to you like this, and this cylindrical this particular coaxial cylinder that we have considered, that is of radius x, and one other thing that we have considered, that it is of thickness dx. So when you look at this, so it will look to you like it will appear to you like this, and this is of thickness dx, and this whole thing of radius smaller, and this thing is of radius x. Okay, so this is what we are considering. Now what we are going to apply, we are going to apply some kind of as already discussed, that we are going to apply some a couple, and it is applied in a twisting couple, which is and it will be applied in a plane perpendicular to its length. So because of the application of the twisting couple, what is going to happen, suppose we will be considering this to be O and this is to be O dash, and let us consider another line parallel to O dash. So it is A and it is B. Now when you apply some twisting couple at the end like this, what will happen? Usually when you see that some wires are there, when you twist it, it comes like this. Okay, so that means initially what was here, it becomes like this. Whatever it was parallel, initially all the lines were parallel to and they were straight. When you apply the twisting couple like this, then they are shifted, this layers are shifted, and it will appear like this. So now instead of considering a curve like this for our convenience, we will be considering as this one. Suppose that after application of the twisting couple, AB becomes AB dash. Okay, and this is twisted through an angle, I will consider this to be phi. Okay, on the surface it is phi, and this angle is also twisted, you see. Now initially it was OB and now it is OB dash, and so angle BOB dash is equal to say theta. Okay, and angle BAB dash is equal to phi. Okay, so here we will be considering that theta is a twisting angle. So what is that theta? Theta is the twisting angle. Okay, now since this particular twist is applied to all the sections of this particular cylinder, so it will be applied to this section of the cylinder also, to the section of thickness dx. Okay, so what is the real picture is going to look, so that I am going to draw here. So it will look like this. Initially it was a center, okay. Say it is called O, and initially it was of radius, say let me consider another big one, that is of radius, okay. So that is of radius smaller, okay, and this is of radius x. So what is going to happen, that we will be considering this of thickness dx. My figure is not that perfect, so whenever you draw for your exams, you will have to draw the diagrams in little bit better way. The notes for this already I have shared in Google Classroom. So here you see this is of x, okay. Now initially what happened, we had a AB here, okay. So let me call it as say B, okay. This position was B. After the twist, it got shifted to B dash, and it got shifted through an angle theta. So this is actually, if you look at this cross section again, now again if you look at this cross section from this side, it will appear to you like this, O B B dash B, and now from this particular thing you can say that B B dash is equal to actually x theta, okay. Now another thing that we need to consider, that suppose that it is diagram, okay, fine. So this diagram, initially it was at AB, okay, then it got shifted to AB dash. So before twisting, just imagine that this is a particular cylinder. If I cut it along AB and if I open it, will it become like an rectangle like this? One side AB, okay, and another side say CD, okay. Now after twisting, what happened, AB is not parallel to O dash, okay. It is now twisted by an angle phi. So AB has shifted to B dash and it is by an angle phi, okay. So obviously that thing will also get shifted. Now you can notice that that before twisting, AB was exactly parallel to O dash, but after twisting, what happens, B gets shifted to B dash. So now the new line becomes AB dash. So as a result, you can see that before twisting, if the hollow cylinder, if you consider this to be a hollow cylinder, if you cut it open along AB, it will be a perfect rectangle. Before twisting, it's a perfect rectangle, but after twisting, what happens, it shifts to AB dash, and this shifts to say AC dash, okay, to an angle phi. So it is not a perfect rectangle now, okay. It has got twisted, okay. This now it has become a parallelogram, and it is AB dash C dash D. So we have two situations, one is before twisting and another is after twisting. So if you look at this diagram, okay, does it look like a shear angle that we have already discussed in class as well as in my previous video lectures? So it looks like a shear angle, as if this top face, instead of the bottom face, this time top face is fixed, and we have applied a twisting couple at the end of the couple, means the moment of the force, okay. So twisting couple we have applied at the lower end, and this is behaving like this. So it is behaving like a shear angle. So shear angle is actually phi, and it is equal to B dash by AB, and B dash, and all of you know that B dash AB is nothing but length of this is the length of the cylinder, so it is equal to L. So therefore we have B dash is equal to L into phi, okay. So now you can see that we have two expressions for B dash, one is L phi, another is called x theta. So we can definitely make them equal, okay, and it will be equal to x theta is equal to L phi, okay. Since we are more interested in the shear angle, because we are given modulus of rigidity. So modulus of rigidity is nothing but normal stress by shear strain. So we are more interested in shear angle. So I will keep phi. So let me mention Yes, shear angle is already mentioned. Shear angle phi is equal to x theta by L. Okay, so this is our shear angle. Therefore, modulus of rigidity eta is nothing but, it is tangential stress. Earlier I have by mistake I may have told you that is normal stress. It's not normal stress, it is tangential stress by shear strain. Okay, so tangential stress is nothing but force applied divided by area. This is the thing. And now shear strain is nothing but the shear angle, that is phi is equal to x theta by L. So we have x theta by L, so that is eta. So if I get F by area, that is eta into x theta by L. Okay, now let it be equation number 1. Now we are more concerned about area. Okay, now, and remember that we are not talking about the whole cylinder now. We are talking about only this imaginary cylinder which is coaxial and which is of radius x and which is of thickness dx. Okay, now when the you know that the twisting couple, that means the tangential force, moment of the tangential force is acting in the lower bottom. Okay, so it is basically acting in the lower cross section. It is basically acting in the lower cross section. Now we need the area. So this cross section is actually the area on which the tangential force is acting. So now in place of this inner cylinder, the cross section that on which the twisting couple is acting is this shaded area. Okay, now how to know the area of this thing? So many people do like this. They will do pi x plus dx whole square minus this thing I already mentioned in class. Okay, so this is so it will be pi x square plus pi dx square 2 pi x dx minus pi x square. So and this one dx is itself a small quantity, so it will definitely become 0. So it is ultimately equal to 2 pi x dx. So this shaded area is nothing but 2 pi x dx. Or you can consider in another way. You just imagine that you are cutting it like this and you open it. So if you cut it and open it, will it become like a strip like this? Okay, so this strip is of thickness how much? Dx. Okay, and this length is nothing but circumference or perimeter of a circle of radius x. So this thing is nothing but 2 pi x. Okay, so length into breadth, this is looking like a rectangle. Okay, so in this way also you can find out the area. So here also area comes out to be 2 pi x dx. All right, so that means in our case f by area is nothing but 2 pi x dx. So eta x theta by L. So we are simplifying the things. So it is pi x theta by L 2 pi x dx. Okay, so let me further simplify it. So 2 pi eta, okay, theta by L x square dx. So that is about the force. Okay, now the problem is that this is the force, this is not the couple, this is not the couple of force. Okay, so how to take a couple of force? That is, it is by taking the moment of the force. Okay, moment of the force. Okay, so moment of the force is nothing but, in one word, it is called torque. Okay, so what we are now, we need to find out moment of the force. So now question is that how to find out the about what? So here you can see that whatever is happening, the only thing that remaining constant is O dash. Only thing that is remaining is O dash. Okay, that is the equilibrium part. So we need to find out what is at the point at which the force is acting. That point is at how much distance from the O dash, that is x. So if you want to find out moment of force, that is nothing but equal to F into X. Okay, so that is again equal to 2 pi eta theta by L. 2 pi eta theta by L. Already we have found force to be equal to this into this. Again I will explain why I am taking moment of force, because we need moment of the force is nothing but couple of force, that is also called torque. Okay, so moment of force actually about what? It is actually about OO dash. Why OO dash? Because it is an equilibrium section, it doesn't change during the whole process. Fine. So now we need to find out the point at which the force is acting. The force is acting in this point. Okay, and that point is at a distance of approximately x from O dash. So that is why we are multiplying it by x when to find out the moment of force. Now what we have? So twice pi eta theta by L, it is now x cube dx. Okay, now this is a moment of the force for this small section, okay, of that particular cylinder, and that small section is of is not the whole cylinder, it is a small part, it is of radius x and thickness dx, that's all. Okay, now we need to find out the moment of inertia for the whole, moment of this force for the whole cylinder. Therefore force for the whole cylindrical wire is, okay, so obviously we need to integrate this. So twice pi eta theta by L, we are integrating with respect to dx, therefore we need to find out the lower limit and upper limit of dx. Now you can see that x is the radius, means ultimately distance of the point from the center. Now you can see that in this particular diagram, come back, what is the minimum value of x? It is at this point, so it is equal to 0. And what is the maximum value of x? It will come up to this point, that is equal to r. So x basically goes from, as per this derivation, x goes from 0 to r. Now if you do it, 2 pi eta theta by L, so it is x4 by 4 and it will be 0 to r. Okay, so we have 2 pi eta by theta by L, and we have r to the power 4 by 4. Okay, and therefore we have 2 this gets cancelled. So pi eta theta r to the power 4 by twice L. So this is called the twisting couple. This couple of force is nothing but the twisting couple. Okay, so therefore twisting couple per unit twist of the cylinder is equal to pi eta theta r to the power 4 by twice L by theta. So what remains? Pi eta r to the power 4 by twice L. So this is the expression for twisting couple per unit twist, and it is denoted by C. Okay, so this is one expression, total twisting couple, and this is the second expression, this is the twisting couple per unit twist. And this is also called torsional rigidity of a cylindrical wire. So this is also called twisting couple per unit twist of a wire, is also called torsional rigidity of a wire. Okay, so that's all for the derivation of the twisting couple. And the same principle is also used for the torsional pendulum. You might have performed experiment for determining the modulus of rigidity using a torsional pendulum. So there also for torsional pendulum, so you basically have a rigid support like this, and from there a wire, and it is with a disc is there. So we usually calculate the time period, okay, total time period. So here also, what is the total twisting couple is equal to pi eta theta r to the power 4 by twice L, okay. So this is a total twisting couple. Now we know that as you know that force equal to ma, okay. The similar analogy in case of angular motion also, what happens, torque equal to I into alpha, okay. Now here in this case, what will happen, torque I into alpha, but alpha means angular acceleration. Angular acceleration is nothing but it is given by rate of change of angular velocity with respect to time. So we can write torque equal to this. Again in this case, total torque is equal to how much, pi eta theta r to the power 4 by twice L, okay. So we can do one thing. So let me do it. That means we have I d omega, let me do it again nicely. We know that twisting couple is nothing but, or torque is equal to I into alpha, where alpha is angular acceleration, I is a moment of inertia. So that is already given. Total is pi eta theta r to the power 4 by twice L, and I and alpha, it is equal to d omega dt. Now you know that this is I must introduce a minus sign here, because it basically indicates a restoring couple, okay. Because you know that whenever because of the elasticity, everybody tries to regain its original configuration after removal of the deforming force. Similarly, whenever you try some deforming couple, it will also apply some restoring couple. So that's why we need to, it is an opposite sense, so that's why we are writing minus sign. Now you know that this thing pi eta theta r to the power 4, we can be denoted by c theta, okay. C already we have written it, and it is I d omega dt. Now we can do d omega dt plus I d omega dt plus c theta is equal to 0, and then we have d omega dt plus c by I theta equal to 0, okay. And this could further be written as d2 theta dt2, because omega is nothing but angular velocity is nothing but rate of change of angular displacement. So d2 theta dt2 plus c by I theta is equal to 0. So from this we can represent, we know that the time period of this particular acceleration will be t equal to twice pi by omega, okay. So twice pi by omega will be nothing but twice pi by, so this is like d2x dt2 plus omega square x equal to 0, okay. So this is nothing but this thing, okay. So omega is nothing but c by I, okay. So from the standard wave equation, so c by I, so we have I by c. So in the laboratory experiments, we always use the value of I and also c. It is pi eta r to the power 4 by twice L, and then it becomes twice L I by pi eta r to the power 4 So if I let me square it, t square equal to 4 pi square twice L I pi eta r to the power 4. So pi so if you know somehow the value of eta, so you want to know the value of eta for a material of a wire, what you need to do, you put it into oscillation and in this particular way, and by attaching a disc to its lower and other keeping the upper half fixed, then find out the time period, okay, find out the moment of inertia and length of the wire, and then you can find out the value of eta, and that is the procedure that is followed in the laboratory experiments. So that's all for couple per unit twist of a cylinder, and also for its application, that is torsional pendulum. That's all for today. Thank you.